to do some extra content. We're going to put in a couple of examples over here because I just want to show you just using a specific example. The one I've chosen here, all right, isn't straight out the textbook, all right? It's a little more complicated than that, and it doesn't follow a sequence of steps. Very often in the problems that we are given, we have a situation where they ask you to work out the potential energy, work out the kinetic energy, etc., etc. I'm not saying it's spoon feeding. I'm just saying that you are being asked to go in a sequence of steps. This example that I'm going to do is not like that. Here's what we are given. A 5-ton truck is traveling at 30 kilometers per hour and wishes to accelerate down a 5% slope, okay, as shown, to 50 kilometers per hour. The relevant coefficient of friction is 0.55. Calculate the power required to do this. Right. So in essence, let's just go through it slowly. This is the, make sure I've got it on black. Yes, I have. This is what we are given. We are told there is a truck at the top there. This truck has got a mass, all right, and it has got a velocity that way. And the velocity at the top of the slope is 30 kilometers per hour. Like so. And then the truck is going to move down the slope to there, and it has increased velocity. So V final, this is V initial, is equal to 50 kilometers per hour. All right? So that is the truck. They've told us it is a 5% slope, which means 5 over 100. Right? Don't stress too much about that. That's just something that I threw in. You'll probably get given vertical distances or horizontal distances or whatever the case might be. And they have told us that the distance down the slope is 500 meters. The first thing I have to do is I have to change my kilometers per hour to meters per second. Right, let's look at that. This comes out to be, what do I do? It's 50 times 1,000 divided by 3,600, and that gives me 13.88 meters per second. And at the top here, our initial velocity is 8.33 meters per second. Okay, well, that's pretty cool. Okay, now let's have a look. What do I say now? I say, okay, cool. I'm going to, just give me a second. I'm now going to say, right, let's put in the forces that we know. Now, remember, what did we say? We said put in the mass first. Right, so I'm going to just put this in down here nice and large, and I'm going to say that is Fg, which is equal to, they said 5 tons. 5 tons, we don't work in tons. We work in kilograms, meters, and seconds. So that's going to be 5,000 kilograms times 9.8, and that gives us 49,000 newtons. 49,000 newtons vertically down. Then they've told us that this slope is a 5 over 100. That means that theta over here is arctan of that. So theta is going to be angle whose tangent is 5 over 100, which is equal to 2.86 degrees. Okay? No, you're not going to get 20s and 30 degrees here in these type of problems, quite obviously, because trucks don't do 20s and 30 degrees for obvious reasons. Okay? Right, so 2.86 degrees, and now we've got that. What did we say next? We said, okay, go back. The recipe says, right, I have to complete the force triangle over here, my 90. This is going to be my mg sine theta, and I transfer my theta there. That is my 2.86 degrees. Can you see it's repeating what we did in previous grades? It's no different. As long as you've got that under the belt, you can solve these problems very simply. So we say, okay, 2.86 degrees. So that's going to be mg sine of that is 49,000 times sine of 2.86 degrees. And then I say, right, that is my force downslope, and it's 2,444.9 newtons. That is F parallel to slope, isn't it? Right. Then they have said to us, okie dokie, therefore this other one over here is the F normal. So, sorry, F normal, it's not really. It's going to be mg cos. I'm just going to put my F normal up there if you don't mind. So I say that is going to be 49,000 cos 2.86. So it's going to be F perpendicular is 49,000 cos 2.86 degrees. And that comes out to be 48,939. So F normal, I'm going to write it here if you don't mind, forgive me. F normal is going to be 48,939. Correct? And the last thing we said that they've given us mu is equal to 0.55. Therefore, FF is equal to mu F normal, which is going to be 0.55 times 48,939 newtons, which is going to be my force of friction is 26,916. 26,916.4 newtons, like so. That's the force of friction. I'm going down the slope, therefore my force of friction, FF, is acting upslope, 26,916.4 newtons. Cool. They might ask you what is the work done by the friction. It's that times the distance. Force times distance is work done, right? Okay, dokes. Now, so we've solved that little bits and pieces. We've put in what we're told. We've got F normal. We've got our force of friction. The last thing we have to put in is, my favorite, is F applied. Right? Cool with that? Okie dokie. Now let's have a look at some more. We know that the power, all right, the power, let's just go back to black, power is equal to work done over time, or equals energy over time, right? Because it's joules per second. That's how we work out power. Okie dokes, what do I do now? Now I go along and I say, right, let's always look at the EK first, shall we? Let's look at kinetic energy first, okay? Look at EK. Doesn't matter which one you look at, right? Doesn't matter at all. Let's look at EK. I say EK initial. The initial kinetic energy is a half mv squared, and this is going to be initial, which is a half times 5,000 times 8.33 squared, which comes out to be 173,472. Whoops, sorry, 173, nope, not going to work like that. Come on, 173,472.25 joules. So that's the initial kinetic energy at the top of the slope. This is what we've got, isn't it? This is our truck, top of the slope. Now he's going to accelerate down the slope, all right? Just out of interest, just have a look at something over here. Please note, I'll show you. Let's just finish first of all. I'm getting a bit sidetracked. EK final is equal to a half times 5,000 times my final velocity, 13.88 squared. So my final kinetic energy is then going to be 481,636 joules. Therefore, delta EK is going to be EK final minus EK initial. Always the same old story, huh? Final minus initial, okay, is going to be equal to 481,636 636 minus 173,472.25, and the number we've been waiting for, turn over my page, is, and believe it or not, yours truly actually didn't work. Oh, he did. Is 308,163. 308,163.75 joules. Let's just stop just a moment here. What does that mean? What does that mean? That means the energy that was needed to accelerate the truck. Think about it. It's the change in kinetic energy. So I had my truck here, and then I put my foot down and I increased the kinetic energy. So the energy used to increase my velocity was that, right? Okie dokie. Now, remember, we also said that F net, we proved this way back, F net times delta x, the displacement, the distance traveled, okay, is equal to delta ek. Remember that? F net times that is equal to that. Therefore, I can now work out, therefore, F net times 500 meters is equal to 308,163.75 joules. Therefore, F net is going to be equal to, just divide that over by the 500, and it's going to be equal to 616.33 newtons. So that is the force needed. This is the force which comes from the engine, force needed to accelerate the van or the truck or the car or the train or whatever, right? Now, what's the next step? F net, the first thing we do, we say, MA is equal to 616.33 newtons. Therefore, oh, hang on, 5,000 times A must be equal to 616.33 newtons. MA, F net, MA, or MA, F net. You always go back to those. Once again, no more rocket science. There it is. So my acceleration is going to be equal to, if I'm correct, 0.123 meters per second squared. Okay, now I just did. Let's do a quick check. Hang on. Let's go and let's do a quick check using Newton's equations of motion, which they've asked us not to do, but let's just do a quick check. So I say, okay, therefore, V final squared equals V initial squared plus 2A delta x, right? So we put those in and we say that's 13.88 is equal to 8.33 squared plus 2 times A times 500. Therefore, I calculate A to be 0.123 meters per second squared. I could have used V is equal to V final is equal to V initial plus AT, okay? And I could have got that, I could have got T out of that, okay? So essentially, I've just plugged it into there. No big deal. Right, now what do we do next? Well, next we do this. We say, right, go back. That's correct. What I wanted to do is I wanted to go back to the top there, okay? Right? I wanted to show you, please look, that the force down the slope of gravity is 2,444.9, right? So there's pulling me down the slope is 2,444.9. How much is friction? Friction is 26,916. Look, 26,916. And the force pulling me down is that. This truck's not going to get down that slope unless he actually gives a little bit of extra vuma, extra power, extra energy, extra force is required. because we're talking forces, to go down there we need an extra force. So what do? I look down the slope and I say F applied plus the weight pulling me down minus the friction must be equal to F net. Isn't that so? F applied plus the weight down, in other words, those over there, those plus there, minus the friction because it's acting against, must be equal to F net. Therefore, I have got this. I can then say, therefore, I'm just going to use mine, F applied, have a look, F applied, okay, plus 2444.9 minus 26916.4 must be equal to F net. Because there is a net force. How do we know this? It's got faster. The velocity increased, so there must be an acceleration. So therefore we say, right, and I know that F net is equal to 616.33 newtons. Therefore, we can work out F applied to be equal to 25,087.43 newtons, right? Cool. So now we say, right, so therefore, what is the work done by the engine? Work done, okay, is going to be equal to, that's the times 500. Work done by the engine is going to be equal to 25,087.43 times 500. Let me just work that out. 25,087, 25, switch it on, 087.43, 43 times 500 is going to be 125,437. 125,437.15 joules. This is my delta X. This is my F applied. The force of the engine, which is enough to get me down there, and the acceleration and everything, is that. This is the total force applied by the engine. Okay? If you just think about these, they're very logical. Right. Therefore, the power is equal to work done by the engine, 125,437.15 joules. Time. Whoa, guys, time. How do I find time? Wait, hold on. I've got here that V final is equal to V initial plus AT. V final was 13.88 is equal to V initial 8.33 plus 0.123 T, correct? Therefore, the time taken to accelerate like this is going to be 45,12 seconds. Okay, so that's my 45,12 seconds. There we've got joules per second. Now the next step is then I say, okie dokes, therefore the power is equal to 278,007.9 watts, and that is 278 kilowatts, right? Now, if you look at the change in potential energy, let's just look at this bit here, all right? Delta EP, okay? EP is E final minus E initial. E final, okay, minus E initial comes out to be, and I did it over here, 1 minus 1,222,444 joules. All I did is I basically took EP at the top, that was initial, and EP final at the bottom is actually 0. All right? Change in is E final minus that is negative. Why is it negative? Right? Because it lost potential energy, didn't it? It came down. So it lost potential energy in the process of coming down. Right. Now, let us turn around and say, okay, let's look, what is that mg sine theta delta x? Okay, just a second. Therefore, let's check this. Check mg sine theta delta x is equal to 2,444.9 times 500, which is equal to 1,222,450 joules. And you'll see it's positive. That is just because I didn't apply the negative to the downslope, right? That you've got the same quantum. This is why I say when you do it, it isn't always just applying a formula. You've got to have a little bit of nous up here, okay? So you can see, yeah, that's the energy, but it's minus because I lost energy. They'll ask you, why is it negative? It's because you lost energy coming down, right? Where did that energy go? It went into helping you get down the slope, didn't it? Okay? Now, let's just take it the same example, because I'm going to do this in the last few minutes. All right? I'm just going to draw it again. All right? Just very quickly over here. All right? Here's our truck. Okay? Same forces are acting. And here's the truck at the top. And it's once again, it's equal to 500 meters. And V initial. V initial now is 8.33 meters per second. And V final is equal to, you see, V final at the top is equal to 13.88 meters per second at the top. All the same applies, the angles and everything. Let's just put it in theta is equal to 2.86. All right. All I'm going to do is I'm going to put in my forces here. Let me now go and put them in red. And this friction's the same number. All I've got here is this, remember, is 2,444.9. Remember, this is 2,444.9 newtons, all right? Then I said, okay, this is going up, therefore, friction is 26,916 newtons acting down. And I then have to have over here a force F applied up the slope, okay? I've put my forces in, etc. Mu k is given again. Now let's start with our kinetic energy again, right? Okay, very simple. Okay, people have said I shouldn't say that, but look at Ek. Okay, delta Ek is going to be a half m times V final squared minus V initial squared. Whoa, you're going, where did you get that from? Guys, it's basically just, it's a half m V final squared minus a half m V initial squared. I just took out a half m as a common factor, okay? So therefore, we'll say that that's going to be a half times 5,000 times 13.88 squared minus 8.33. And we know this answer is going to be equal to 308,163.75 joules. What does that mean? That means, quite straightforward, we have gained energy. We've had to put energy in to do that, right? Then we say, okie dokie. The next step is we go back and we say, right, F net times 500 is going to be equal to 308. Can you see it's just the same step, isn't it? 0.75. Therefore, F net is going to be the same. 616.33. 0.33 newtons. Why would you expect F net to be that? Well, it takes the same energy to accelerate me whether I'm going up or down, doesn't it? Do you care if it's going this way or this way? No. Therefore, you don't care if it's going down the slope or up the slope. The energy needed, it's purely to accelerate this mass. That's all we're looking at. We're not looking at energy of potential. We're not raising or lowering with this one, right? We're only looking at the acceleration of the body. Therefore, okay, now we look upslope, okay, right? We say, right, look upslope as, say, positive. Remember, we've done this before. We say, therefore, F applied minus 26,916.4 minus 2444.9 must be equal to 616.33. Why? Well, F app is upslope. The others are all pulling back. Right? Therefore, F applied is going to be equal to 29,977.6 newtons. Right? Therefore, this is the force applied by the engine. Force applied by the engine. Let's just go back to the slope of mine over here, shall we? All right. What does this force have to do? Go to blue. This force has got to be enough to overcome that. It's got to be enough to overcome that. And on top of it, it's got to be enough to accelerate me. Correct? That's what that force is doing. It's overcoming friction and the weight down, and it's accelerating me. Okay? Let's move up a little bit here. All right. Therefore, we go through the same process to work out time as we did before. Therefore, power of the engine is going to be equal to, the work done by the engine is going to be 29,977.6 multiplied by 500, which is going to be equal to 149,888.15 joules. Divide that by 45.12 seconds. It's the same as previous, okay? And that gives us 332.2 kilowatts. There you have it, right? So in these problems, okay, they're going up or going down, the slopes of vehicles. Just approach it in that way. You are familiar with it, right? So it makes a lot of sense. Thanks for watching this. The next stage I'm going to do is I'm going to look at vertical motion, where we're going to go up, we're going to go down, and we're going to look at some air resistance problems or problems where we hit things on the way up. All right? Essentially, we're going to be looking at the conservation of mechanical energy. Right? We have spoken about this in previous years. We're going to come back and revisit it. Cheers. Have a good one. Go through those and enjoy them. Think up some of your own. Just go through the logic. Seriously, if you need to, buy a car. Well, not really, you know what I mean. Or use a box. Just think about what's going on with this. The moment you see it in your mind's eye, man, it makes all the difference. Cheers. Have fun. Bye.